Hello everyone, welcome to a problem session. This is a very standard problem that we encounter. It's just question about definition, being clear about definition. So this asking, do we know what we mean by efficiency of a thermal engine, of a thermal power plant engine, power plant. That's power plant contains an engine which is producing energy. So this is one thing, and usually this gets confused with the most efficient engine possible. Okay, so efficiency of an ideal, also called Carnot. T is silent here. Engine. So these are not the same things, but they usually get when the professors make up this question, they're trying to see if you know the difference between them, because they're not the same thing. So let's see what's going on in one. Efficiency is basically what you produce over what the cost was to produce that. Okay, so that's efficiency, and this is actually is written in terms of temperatures that are involved. The highest, so this is a ideal, and you might have seen this 1 minus the core temperature in. Okay, so this is the ideal, and this is always the case. What you produced versus how much it cost. So here we're talking about thermal efficiency of a steam engine. So what's it probably useful to kind of know what the steam engine looks like. Okay, although you may not need much to solve this problem, but let's understand. So this is aside, but I think it's kind of important to know some basics. So usually you have some boiler, and it will have some water in there, and you have some fuel. Let's see, this is coal, and you're gonna heat it. So this is going to be some kind of heat will energy will go inside, and this will make it a steam, and then you have steam that will go. I mean, this is much more complicated than this, but basic physics is very simple. It goes in a like a multi-stage turbine, which rotates the whole structure. The steam pressure rotates the structure, and this structure can rotate a magnet and then produce current. So you have a current come out. So this is where the work is out, and then what happens is the steam here becomes moist and some liquid, something like that. So the steam then kind of makes its way to a pipe and some condenser. This condenser, where it will condense to some liquid water, and so between here and here some heat has to come out. There's a cooling mechanism, usually maybe cold water is applied to it, maybe this pipe goes in a river, and the river water just flows over it. So heat comes out of it, heat goes into it, and then this water, let's say this water is kind of pumped into the boiler. Okay, so this, if you look at it, this system, we're going to call this much water, goes through this cycle. Okay, so this part, we just say Q H or Q in. This part is called QC, and this is the energy that's out, energy that's taken out, like work is, so like electricity or something like that, it is called work, W. And if you look at in a full cycle, this full cycle of a steam, so in full cycle of water here, which is liquid and steam, you know, in full cycle of water, QH in, QC out, and W out. So this much energy is, so energy balance, you'll say QH, positive, negative, whatever you want, make sure everything is fine in terms of, so that will be the energy balance. So when you look at produce, you just produce this is produced, and this is the cost, because that's what you heated. This, you used all this coal, or you know, a nuclear works this way. So your efficiency will be W over QH. Okay, it turns out that this whole thing sometimes is very inefficient. So if instead of using a steam engine, you ran this with ideal gas, and this, you run exactly like this, but ideal gas, and a particular cycle in which you didn't allow for any loss of friction or anything like that. So so if I use ideal gas, and you went through various processes which we can draw in a PV diagram. So say you start with some point, and you heat it at a constant temperature. So let's see, this thing was at some temperature TH. So I heated TH, and so we follow this isotherm, so point A to some point B in the ideal gas. And then you did lower the temperature by expanding it adiabatically. So this adiabatic, so this will be a lower temperature, T sub C, and you use compress. Now compress at constant temperature Tc. You come to some point D, and you come to a point where you can, if you do it adiabatic, you get back to the original. So you choose a point to come to where you if you do adiabatic compression, you come to that point. So this cycle is called Carnot cycle. And if you work this out, then QC and QH in here can be shown to be proportional to so here you can show that QH is proportional to TH, and QC is proportional to TC. And in here you can see that this W I can kind of replace by W will be QH minus QC, right? So if I replace over here, you have a QH minus QC, assuming QC to be positive. So just if you don't like positive negative sign, then you can just look like that, and you can see that this is 1 minus QC over QH. So if I you can be shown in ideal gas. This is how actually you define what the temperature, absolute temperature, looks like, by having this proportion for the ideal gas. So for the ideal gas, this will turn out to be this formula. Okay, so that's a brief review of this, and this is the maximum you can. So this is the max you can get, and this would be what will be actual. So I'm going to erase this. I'm going to apply that to my system here. Okay. So in here it says it for every minute. So you got to really make sure you understand this. So if every minute you it outputs this much energy per minute. So let's do everything in a minute, right? So W, so in 1 minute, that would be fine. 1 second, 1 minute, if you want to do. W is 180 megajoules. So let's make it 1 second. In 1 second, W will be, so the power and energy will be same number. If I do in 1 second, right? That's divided by 60. This will be this will be 1 over 80. This is capital M over 60 and this will give me 3 megajoules. Okay. So this is W. In 1 second, it's using 18 kilogram of coal in 1 minute, right? So in 1 minute uses 18 kilogram of coal. So that means in 1 second uses 18 over 60, 0.3 kilogram of coal. So this, how much energy it says for each kilogram it has this much energy in coal. So it will release 0.3 times 30 megajoules of energy. So this is 9 megajoules of energy it will release, right? So this would be QH. So take a ratio of these two. So the efficiency, usually is later eta is used for efficiency. That's the symbol normally used. So this much produced, but used up this much. So 3 megajoules produced, 9 megajoules used up. So this is 1/3. Okay. So this is the answer. This is the answer for 1. This is the answer for 1. So 2, it says that if I use a Carnot engine, where the high temperature of the cycle is this and low temperature is that, then what will be the maximum efficiency of that Carnot engine? So I just use this formula, but I make sure that things are converted into Kelvin. So this will be eta ideal will be 1 minus Tc in Kelvin, Th in Kelvin. So Tc is given in degrees Celsius, so I need to have 27 plus 273. And Th is given in 527 plus 273. So 1 minus 300 divided by So this is 600. So 1 minus half is half. So that's the maximum efficiency possible, but this is the actual efficiency for this power plant. Now notice that when I was describing power plant, I gave you all these temperatures, which you didn't need. Over here, you didn't need. You need the temperature only in the case of when you use idle engine, right? So this is where the confusion takes place when student is given some extra information, and when trying to solve this number one, efficiency of the power plant has a lot more information. Suppose I didn't have this. Suppose I didn't have this part. I didn't ask you this part. Okay, then you would be done here, right? And you would not have used any of the temperatures, and that's where the confusion comes from. That's one confusion. Second place I find a lot of students get tripped up is right over here. Right over here. They forget to convert. Convert this. So this is not equal to 1 minus 27 over 527. So this is another place people can get tripped up. Otherwise, this question is very straightforward, and I don't know why it makes it in a lot of tests. There is a similar type of efficiency in a reverse way that happens. For instance, when you're trying to cool something, and that's called refrigerator. So you're in a refrigerator, you can also say what is the coefficient of performance. The efficiency is called coefficient of performance. Means you want, in a refrigerator, you want your energy that you're going to use up should be the least amount, right? So your cost is not like QH, your cost is the W, the work you have to do, the electricity that you have to supply. So while the efficiency will be always less than equal to 1, but coefficient performance will be greater than 1, and so you want to be able to have highest performance, cost of performance. Maybe I'll do a video about refrigerator, okay? But in the refrigerator, there's a very similar concept of what you might call efficiency of a refrigerator, which is not called efficiency, it's called coefficient performance. And there also you have to have what's my cost and what is my goal. My goal is to reduce the temperature of the inside of the refrigerator, right? So there's outside temperature, there's inside temperature, and then there is an energy that I have to use to achieve lowering the temperature of the inside of the refrigerator. Okay, so if you get a chance to read on that, go ahead and all right, I'll see you in another video. Take care. Bye.